Okay, I hope you can hear me. So we were doing generative modeling with optimal transport. So in the last class, we have developed quite a bit, and the main idea was if we look into the Wasserstein distance or the generic optimal transport problem, then it's of the form minimize PQ, and the cost can be written as a inner product of the cost function C and the joint probability with the marginals P and Q. And we are supposed to minimize this cost. This is a generic formulation. Okay, so here if we write this explicitly, expand the inner product, then this is sum over C xy by xy and over the points xy. So this is the expanded form of the optimal transport cost. And then the whole goal for the last class was, is there a good way, faster way algorithm to compute these costs? Okay, because these costs are useful because they tell you how to compare two distributions. Okay, so if you have some estimate of your distribution and some parameterized distribution that you generate, and if you have a faster way to compute, then you can tune the generator that is generating the Q, and each time you compare, and then you allow the gradient descent to update the parameters of your model. So this is a direct approach. I say it's a direct approach because I look directly into the loss function and update the parameters, whereas in WGAN we had to formulate the duality and so on. Okay, so that's the thing that we did in the last class. So and here we put a generic cost, but if we put C xy to be norm of x minus y, let us say one norm, or I mean it doesn't matter. Okay, so it's basically it's a two norm, but okay, let us say if we put one norm or two norm. Okay, but then we can have some specific variant of this. Okay, so in this case we can keep choosing specific C, and depending on that we will have a way to compare these two. Obviously it has to be some form of a norm. Okay, so so we did quite a bit in the last class, so obviously we don't have to. So what we want to know from here is what is an algorithm that can compute this quickly. Okay, and this is what we developed in the last class, and that was our primary algorithm, we would say. And there is a faster variant of that we want to do today. We could not complete it last time. So we followed some process before we could do this. So first thing we noticed is it is easier, or it's more let's say convenient in the sense of the algorithm, that we add some convex regularizer. Okay, that makes this strongly convex. So this is called entropy regularized OT. So right now it's OT. Okay, so optimal transport. So this is called OT, but then if you add some regularizer here, then it's called entropy regularized OT. So entropy regularized OT essentially just tells that you add certain regularizers, so then this will change to, this is the regularization parameter and PQ, and we have cost C pi and minimum over all the joint, and then plus you add this entropy, so-called entropy regularizer. Okay, so this is entropy function. Okay, that's what I mean. It's called, and the way it is defined is it's like pi log pi. Okay, but then it's in the form of a summation because you have to do this as a sum. So this is like pi xy log pi xy. Okay, so this entropy regularization helped in the algorithm. Okay, in the sense that overall it became strongly convex. So we saw in the last class that h, or it was I guess minus, I guess. So the negative of the entropy is strongly convex. Okay, entropy as such will be, so the way it is defined would be like here, and then minus minus will make it plus. Okay, so negative of the entropy is strongly convex. Okay, and we have proved that it's strongly convex. Proved that H is strongly convex. We have proved that H is strongly convex, and the fact that it is with the linear is also strongly convex. So linear plus strongly convex is strongly convex, and subsequently we have shown that that all this follows from the basic foundations, then that the existence and uniqueness of the solution of this. So this being strongly convex, there is a guarantee of unique minimizer. So strongly convex guarantee unique minimizer, and existence of the minimizer is given by the fact that pi, the set of pi, these are with further restrictions that marginals are p and q. So the set of pi pq is a compact set. So I'm just doing this quick review here. Okay, we have done some of these proofs already, and strongly convex implies continuity. Continuous function on a compact set attains its extremum. So there is existence of the minimizer. Strongly convex implies uniqueness. If there is existence, then it says there is a uniqueness as well. So all these nice features you get via this entropy regularization. So that's the motivation behind entropy regularization, that these are the features I get. The next key idea, so this we can say that the key idea one. Okay, so it's also good to kind of track what are the key ideas, right? So this is well-known problem. Okay, 1930s or even before that. This is the key idea one. Do entropy regularization. So by so these are like Kuturi, okay, around 2015. And then the second key idea came from the fact that I could somehow bring in the KL divergence here. Okay, and the KL divergence will be used as a metric, and this metric will be used to do alternating projections between the two set of marginals, which are the affine sets here. Okay, so the next key idea came from bring in KL, or formulate it in that way. Okay, so somehow, like when doing research, you might think in this way. Okay, so with this, is it possible to bring in somehow KL divergence, because that's a well-known divergence function that we are familiar with. So the key idea there came via KL divergence, and then the form of that was and to do that, you as such, you may not see KL divergence as such straight away, but you created a distribution for which KL divergence will show up somehow. Okay, So not in the current form, but we created a distribution, so-called Gibbs distribution, and then it somehow appears here. And the idea there was you defined a function kxy, which is exponential of minus c xy divided by lambda. So all this is known. Cost c is known, c of xy is known. You can compute that at each point xy. Lambda is the regularization parameter. And with this k, you defined a z. So basically you create a distribution from here. So basically you normalize this, right? These guys are positive. So I can create distributions in a way that I just keep the entries positive and the sum of this is 0. So how will I do that? I will normalize this by the same guy, meaning that in the denominator I will sum up these values, so that eventually if I sum up, numerator sums up and denominator is already summed up, so the total probability should sum up to be 1. Okay, so that way so right now k is not a distribution, but we want to transform k into a distribution by proper scaling. Okay, so that proper scaling was done via z. So we just summed up, right? So that's a very common way to do things. Okay, create distributions like that. So we have a normalization factor, basically normalize, right? And then the new distribution that we get, we call it p lambda k, which is kxy by z lambda. So if you look at the vector p lambda k, then the sum of the p lambda k is 1, and p lambda k entries are all positive, and that's the criteria for a distribution. So-called Gibbs distribution we have created, and now we brought this p lambda k so that somehow k divergence will show up. Okay, and then we looked at what exactly this k divergence, let us say, is with this p lambda k. So we just looked into this. Okay, and we said that okay, we have created a new distribution, but let us compare it with the joint distribution pi. And we did some calculations, and we got the value 1 by lambda c pi minus h pi plus log of z lambda. Okay, and we did all these derivations, and so from here what we see is that we got some relationship between d lambda c, because we see c inner product of c with pi popping up there. Of course lambda seems to be misplaced, but if I take lambda 1 by lambda common, then everything seems to be in place, because c 1 by lambda taken common, then I have just c pi minus lambda h pi plus lambda log z lambda. So it has these terms that we wanted with additional log z lambda term there. So but what was interesting is if I'm looking for minimization, then log z lambda has no role to play. Okay, because log z lambda has nothing to do with pi. Okay, remember that z lambda is defined on k, and k is based only on the cost. Okay, so z lambda has nothing to do with so z lambda has no dependence on the joint distribution pi. Okay, but it just depends on the cost. Cost has nothing to do with the pi. So essentially what it means is that the arc min of this, if I'm supposed to do minimization over pi, it should be the same as this, because the constant will not play any role, because log z lambda is like a constant with respect to pi. So minimizing d pi p lambda k is same as minimizing d lambda c p q. The minimizers will be the same. As I said, you take 1 by lambda common, because 1 by lambda common, you get the same thing with the additional lambda. So 1 by lambda and then c pi minus lambda h pi, and then that's it, log z lambda. So minimizing d lambda c, the pi at which this lambda c will be minimized will be the same pi, because 1 by lambda constant factor doesn't change the place where the optima achieves, and the constant log lambda also doesn't play any role in where the minima is achieved. In other words, in optimization we say that both are equivalent optimization problem. Okay. So this was the idea number 2. Okay. Idea number 1, entropy regularization. Idea number 2, bring in the Gibbs distribution and create an artificial distribution, and then relate this to the KL divergence, and then you will now minimize the KL divergence. Okay. So then the third idea is kind of algorithmic idea. The third idea says that I'm looking for distributions, joint distributions, whose marginals along one of the dimension x is p, another dimension is q. So this is now an algorithmic problem in the sense that I can see the set of distributions pi p q as intersection of the sets whose marginals is only p and whose marginals is only q. So hence we break this set as an intersection of two convex set. In fact, those are affine because the pi p and pi q constraints are affine constraints. So the idea number 2 is algorithm idea. Okay. Basically, I want to minimize d pi, and so this essentially belongs to algorithm. So now here you see this set pi p q as a intersection of p intersection of q. Okay. So that's our third idea, and this happens to be our final idea. So it says that joint set of joint distributions marginal p and q must be the intersection of distributions with p and with q. Okay. So then, and what we notice from is that these constraints are affine set. So in more specifically, these are convex. So affine sets are convex. So convex. So it's the intersection of two convex sets. Basically, we want to go to the intersection of two convex sets. Okay. So we may start with pi p and pi q separately, and then our goal is to kind of go there into some intersection point here. Okay. That will give me a pi for which which is a joint with both p and q. Okay. So it's kind of an alternating projection idea. Okay. Or sometimes there are other ideas like alternating minimization, but that is a little bit different than this. So here we are doing projection. So if we have sets like this, and if they intersect, then obviously, I mean, there is a proof that it will converge for convex set. Okay. We didn't do this proof, but there is a proof for this as alternating projection. I have that proof, but I will skip that. And in cases if it doesn't intersect, it could be interesting because it will help you get separating hyperplane as a outcome. Okay. So in case they don't intersect, we believe that in our case, in the optimal transport, they will intersect, but this is a little bit of a diversion here. So even if they don't intersect, what might happen is that they will do like this, and it will stay there, because after that there is nothing more to do. So this will be your x star or y star, and then you get a separating hyperplane. Basically, you can build a classifier out of this. So make a normal, so take a plane which is perpendicular to this, and this separates the two sets. Okay. So even if they don't intersect, also it's interesting algorithm. So, so this was the key idea, and we followed algorithmic procedure, meaning we started with some pi. Initially, we don't know, obviously, so we will start with something something random, and but obviously, that pi will be the distribution whose marginals will be q, obviously. Okay, so we have to start with a pi whose q was a row sum. Okay, so like this. So these are joint distributions, right? So these are tabular data. You should always have this picture in mind when you look at the pi. Pi is like a matrix. Okay, we are updating matrices. Okay, so we are essentially looking for an optimal pi, and so we will start with some distribution which only satisfies. So let us say if this direction is p, p1, p2, p3, p4. And so these are like the row sums, and the column sums are q1, q2, q3, q4, q5. So what this algorithm says is that you bring in any distribution whose at least the row sum is this, which should be a bit easier, okay, to start with. And once you first start with that, and then you project it on the set of distributions for which you have this marginal, and so on, and eventually it will converts to a case where both row and column sums are p and q. Okay, so this is the algorithm, and so we did this derivation using Lagrange multiplier and so on. So obviously we don't have to spend too much time on that. We will write the iterations, the final iterations that we derived in the end, right? So we call this even iterations and odd iterations. We can call this even odd sets. Okay. So, and then we wrote these iterations on how you will run these iterations as an algorithm. So the even iterations are diag of p by pi 2l minus 1 lambda 1m. It's a vector of all ones. Okay, so this is pointwise divide. Okay, this is a vector, and this is a matrix times a vector of all ones. So basically it's a you multiply a vector on the right, so it does a row sum. Okay, so it's a row sum of this, and this is a vector, and this is p. So after doing row sum, you will get in this example like 4, so it's length 4, and after row sum it will be length 4 after row sum. So length 4 pointwise divided by length 4 vector, ith entry divided by ith entry. Okay, and then you make, and then overall it's a vector, but you make a diagonal of this. Okay, because in the end you want matrices to be iterated. Okay, so overall this tag means make a diagonal matrix with on the diagonal you put this vector. Okay, so and then we had pi the old one. Okay, so 2l minus 1, the odd one. Okay, so as you can see, there is everything here for you, known for you, because when you are computing Wasser size distance, p and q obviously will be given to you. So you know this p, you know this q. Okay, and then you calculate this to update this, and the next time the odd iterations will be pi 2l plus 1 lambda is diag of q by 1, and we did this derivation, so you can watch the videos if you don't remember. Then pi 2l lambda. So as you can see, all the data is there for you. As an algorithm, it's a very simple algorithm. You can kind of iterate over this. So obviously your first question would be, what would be the initial? The initial, you choose anything you want. Okay, that's fine. So it will eventually converge. I mean, with the constraint that its marginal is, the odd marginal is q and even marginal is p. Obviously you cannot start with completely random thing, right, because it's about projections between sets, so it has to come from pi q or pi p, it doesn't matter. So this is all we did, and then so this is one algorithm to compute. Okay, but there is a little bit high computation cost involved here because we are dealing with matrices. So the next algorithm is something called Sinkhorn algorithm, and that iterates on the vectors. Okay, so it's a very simple idea. So we will try to wrap up that. So that will be the, I guess, the most optimal algorithm for computing persistent distance. So the next step is a Sinkhorn algorithm, which is just another algorithm for this. Okay, there is nothing new here. Sinkhorn algorithm. So Sinkhorn is the name of a person. So previous algorithm in the last class iterated on pi. Okay, so the previous algorithm iterated on pi L lambda. I mean, you can call L as 2L or 2L minus 1, it doesn't matter. And we can iterate more efficiently if we use some other variable. Okay, so can iterate more efficiently with some choice of vectors. Let us write a proposition then. The key idea here is that it could be transformed into something called scaling problem. Okay, so given a matrix, how can I scale row and columns, okay, such that it satisfies row sum equal to something, column sum equal to something. So there is a generic problem here. It's called matrix scaling problem, and that's the motivation behind Sinkhorn algorithm. So let us see what is that. So so this is given by this proposition. So let K be some n by m matrix with the entries of K defined by kxy, which is xy. Okay, so if you prefer ij entry, also you can do that. So xy is the entry, and for some u which is length n, and some v which is length m, we can write pi lambda as diag of u k diag of v. Okay, so this is a proposition that says that the joint distributions can be seen as some simple scaling of the K matrix. Okay, K is the same K that I wrote on the right side of the board, exponential of minus cxy by lambda. Okay, so it says that, and this view helps us because later we will see that the iterations will run on u and v vectors, not on pi, which will be a benefit compared to this. So let us prove this. It's a simple proof. So now recall the Lagrangian that we wrote. Okay, that was in the proof while we were doing this. So I will write down the Lagrangian that we had before. So the Lagrangian that we had was on f, and with the Lagrange multipliers f and g, which corresponds to the marginal constraint being p, and g corresponds to the Lagrange multiplier marginal constraints with q. And we wrote it as c pi minus lambda h pi plus f p minus pi 1m. Okay, there is already a video, so you okay, so plus g q minus pi transpose 1n. So this is the Lagrange multiplier. I mean, this is very evident, right? The problem we were solving was minimize this guy, the entropy regularized one. Okay, and then these are just the Lagrange multiplier with the constraint that marginals are p and marginals are q. And as a next step, we try to kind of infimize over the primal, which is pi here. So for that, we will take a derivative with pi and equate it to 0. Okay, so that's the next step. So so we do this. So del L. So that's the usual way to solve optimization problem via dual. So pi f g. So the first step for you is to find a minimum of L with respect to pi, and that you will get by taking derivative with pi and equating to 0. So this is after derivative, and we can do this element by element. Okay, so we can do this for, as we did in the last class also, we can do this for some fixed x and y, and this will be lambda. Yeah, because that's right, because the first term, if I fix x y, then h pi will be pi x y log pi x y. So if I take a derivative, what do I get? I mean, we can expand this and write, okay, but let me write down the answer and then I will justify all of these. So c x y plus lambda log pi x y minus fx minus gx, and this must be equal to 0. Okay, so let us see how we do this derivative, right? So see, this term seems to be okay. So let us say this is our first term, and this came from the derivative of this guy. So that is settled. So derivative of c transpose pi is just c. Okay, and then the entropy term lambda h pi, that goes with this guy 2 2. Okay, so this is of the form lambda, I mean, just look at this term, then this is pi xy log of pi xy. So if I take a derivative with pi, then log of pi xy. So then you have this term pi xy and derivative log sorry, this term. So pi xy and derivative of log pi xy is this term lambda. Yeah, we are wondering where is the, yeah, I think we did the minus also throughout. But anyway, so it should have been minus lambda, I see. But then how come the cost remained plus, right? Now h was minus already. Yeah, sorry. Yeah. So whole thing, this was minus. So minus must become plus. Okay. So all this is fine. So first function derivative of the second. So that gives me 1. So just lambda remains. And then second function derivative of the first. So derivative of the first is just pi. So that goes away. So just L lambda log pi remains. And then the remaining terms are also kind of straightforward. So this is f transpose times pi is only here, and you are picking only the x y term here. So f will only go with the x y term here. Anything other than x y remains. It's a constant with respect to, because we are only working with x y right now. So hence I just denote that as f sub x. Okay, it's not like fx, but it's f sub x. That denotes the x component of that inner product of f with p minus pi 1m, and similarly for the g term here. Okay, so that's what we are supposed to do when we solve via dual. So we are supposed to infimize L, and then we look for pi for which this optimality is achieved. So then so I guess we will solve for the pi. Okay, so solving for pi xy, and then it will be, let us do this first. So pi xy. So and then this is we just write a first step, and then what I do is that I split lambda into half, lambda half. Okay, so lambda is equal to lambda by 2 plus lambda by 2, just to make things a little bit symmetric in the equations later on. So I write this as minus half lambda minus cxy. Okay, and then I divide by lambda throughout. So pi xy is fx by lambda plus gy by lambda. Okay, but one more step was like I will take the half here as well, minus half, group them, plus gy by lambda minus half minus c xy by lambda. We divided by lambda and we did some grouping, and now we will solve for the pi lambda, pi. So this implies pi xy is equal to e to the fx by lambda minus half e to the minus c xy by lambda and e to the gy by lambda minus half. Okay. So as you can see, the scaling has been achieved. Okay, because what we were looking for was the k. K is right there in the middle. The k which we define is on the right right side of the board. Kxy is defined, so the k we derived here exactly, and on the left side we will take it as a u. On the right side we take it as a v. So in the vector form, if we vectorize this, it will become like diag of u, k, and then diag of v. We have to make this as a diag because it's multiplying entry wise, so we have to make this as a diagonal so that it goes with xy. Okay, we don't have to keep it vector, otherwise it will sum, right? The goal is not to sum. So basically we will take diag u, k, diag v. Okay, so what is the conclusion? Conclusion is that for the choice of k we have, for the regularized OT problem we have, such scaling exists. Okay. Now this problem in itself could be a generic problem, which goes into something called matrix scaling problem. Okay. So you can find one chapter in itself on matrix scaling. Okay. So you can have different scenarios. Okay. Given some other distributions, another type of k, okay, for another problem, then you may have to find a good scaling factor. Okay. So advantages of this is that your joint distribution could be seen as some factored form, which can help in algorithm, like I will show you now. So we will build an algorithm now based on the fact that scaling exists. Okay. So let us build an algorithm based on this idea. So we know that the joint is of this form, and we also know the constraints on the joint. It must match. It must be the marginal. If I sum over y, it should be p. If I sum over x, it should be q. So this is an additional constraint that will help in the algorithm. So, and a more generic statement, if I have to say, I can also relate it to p tensor q. So look at p tensor q. So p tensor q is an operation defined on two vectors. So let us say I have vectors p1, p2, and so this was p was n, I think. Okay, and tensor with q. So q1, q2, qm. So if you look at the tensor, and what we will get, right? So we will get like it's an outer product basically. So we will get p1, q1. So p1, q2. Okay, if I have to, maybe I should have written horizontal, but it doesn't matter. Okay, so let us say it's outer product. Okay, so the whole idea, what I'm trying to say is that it's also, I mean, if I see p outer product q, then if I start adding the row wise, then it's exactly what I get p1, because the sum of qis will be 1. So that's what we are going to get as an interpretation of row and column sum of this are also p and q. Okay, so this is p1 qm, and then p2 q1, p2 q2, p2 qm, and then we have pm q1, pm q2, pm qn, pn. Okay, so we have to make it, so p goes to n and q goes to m. Okay, so this is an outer product operation defined, and if I look at the row sum, then row sum comes out to be P1. And second row comes out to be P2 because P1 you take common and sum of the Q must be kind of, these are like Q is also a distribution in itself. So sum of the Qi's will be 1, sorry. Sum of Qi's is 1 and it will just be P1. Second row sum will be Q, sorry, yeah, P2. So the first row sum is P1, second row sum is P2, so it's Pn. Similarly, if I do the row wise sum, then what we get is Q1, Q2, Qm. Okay, so what we are essentially, another way to say is like the pi that we are looking for should have same row sum as P outer product Q. Okay, so essentially it should have similar properties in the sense of row sum and column sum. So I have in the passing I have said metric scaling, so I will just write down a line about metric scaling because it's a it should be in the notes, I guess. So metric scaling. So in the discrete case, metric scaling problem okay, just formally I'm just writing these things. So metric scaling problem is about finding U and V that scales rows and columns of K such that it matches the row and column sum of such that it matches the row and column sum of the given distribution P and Q. Okay, so that's the problem of metric scaling. So if we come back to our case where we are working with this pi, then the constraint is that the diag of U, K, diag V must be P. Okay, so in our case, what we want is P is pi times 1m, which is the row sum, is which we have seen that pi is diag of U, K, and so on. So we replace that pi now. So U, K, V. So since I multiplied by once on the right, now this became a vector. Now this is no longer a diag of V. Okay, so that's the change happened because of multiplying by 1m. And then Q is pi transpose 1n, and this is diag of V, K transpose U. Okay, so that's the effect of multiplying with the transpose. Okay, and because I first did the transpose, so U diag U went to the right, and we had a K transpose, and V came in front. So now the diag U changed to U after multiplying by 1n. So the Sinkhorn idea is now just basically one line. Okay, it says that so we can, although it's one line, we can still like maybe write it here. So approximate solutions to this, guys. Okay, so let us say this is our star. So approximate solution to star okay, by initializing, U you start with u, which is 1n. So sometimes this is called like defined, okay? So u is defined like this. I put it three horizontal lines, and v is taken set to be 1m. So this is what initial iterates we define, and then the algorithm says that you update ul plus 1 as p by kvl and vl plus 1 by q by k transpose ul plus 1. Okay, so that's it. The algorithm tells that we are just supposed to do this, and this will produce the same iterates as the previous one. So a minor check that we will do is to really convince that this is producing, this is equivalent to what we did before. Okay, so that's the proof we will do to verify that these iterates are similar to the iterates we are. This is just an alternative way to solve the same problem. So what we want to say is that the way we will prove is that we can show that these iterates will also produce the iterates that we had before. So that's the final check we will do on this algorithm to verify ourselves that this is indeed a correct one. Okay, so the claim that we will make, as such algorithm is there, you can compute the Wasserstein distance iteratively. Okay, that's it. You don't have to do much. Cost function is given. The K matrix you know. Okay, the OT problem is given. You consider the entropy regularized one. Lambda will show up. From the cost, you construct this K matrix as exponential of what was that, x? Okay, I almost forgot, sir. Minus Cx by lambda. Okay, so this is the matrix you create because it's a discrete case. So xy number of points this. So k is finite, and then you will have some m by n matrix. K is there. Lambda is usually a hyperparameter, so you will fix some suitable lambda. So k is in hand. U and v anyway start from something vector of all ones, and p or q are distributions that you are asked to compare with. So algorithm is very straightforward. Everything is there in hand to compare two distributions iteratively. Okay, so it should be u of l, right? Yeah, it should be depend on the previous one. Yeah. So let us prove that this iterates are, although we have written, it seems like out of nowhere, right? So that's the thing. So we want to verify that because at least for the previous one we did some derivations, but here it seems like it came out of nowhere. So let us try to prove that this is similar to what we had before, but the only thing is like now we are running these iterates on vectors, and previously we were running iterates on the full joint distribution, which was a matrix. So let us prove this claim. So with these choices of the iterates, with these choices of the iterates ul and vl, so with these choices of the iterates ul and vl, we obtain, we call that primal iterates. Okay, the first one that we had. Okay, so we usually call them primal. So we obtain primal iterates. Okay, so we will verify this. So let us do this. So to prove this, so to see this, we run the primal iterates. Primary iterates, which are pi 2l. Okay, so even odd things. So pi l 2l and pi 2l plus 1. With these choices of ul and vl. So why you would do that? Because we had a proposition before that that said that there is a existence of So pi was diag of u k diag of v. Okay. So the idea what we are trying to say is that we know this relationship. So what if I plug in these u and v that I am proposing here, and with those choices of u and v, will I retrieve the iterations that I was getting for the pi? Okay. So we are supposed to do that. So with these choices of u and vl, and let us say this is like a double star. In double star, and just to like make it a different notation, we will use tilde just to keep it separate from the primal. So we will now start using tilde, and we will show that these tildes are the same. Pi tilde is same as pi. That's what we are trying to show. Okay. So we use notations pi tilde 2l and pi tilde 2l plus 1. So using the definition of the primal, which we have proved in the proposition. So from previous proposition, we start this substitution now. Okay. So from previous proposition, we had the definition that so the pi tilde will be diag of u k diag of v. Okay, this is something we know. Now we will now split them into odd and even. Okay, so splitting them into odd and even, then we will call them. It's a notation thing. It doesn't matter which one you call odd or which one you call even. So, but let us fix something. So let us say this is our 2l, and we identify this as even iteration, and this is diag of ul plus 1 k diag of vl. Okay. So what I'm saying is that I'm generating even iterations like this. Okay. So and then I will generate the odd iterations like this, and ul and vl are being generated by that. So overall, if it comes out to be the original pi 2l form, then I know that both algorithms are generating the same stuff. Okay. So 2l plus 1, I denote this as diag of. So in this, so this is ul plus 1 k diag of vl plus 1. Okay, I'm a little bit doubtful about that double star, whether there was l or l plus 1. Okay, so I will come back to just verify this. Okay. So because looking at here, it seems like anyway. So this we define it to be k diag of vl plus 1. Remember that this is something we are saying. Okay, we are saying that if I take this, then I will prove that this will be original pi. Okay, so the choices that I am taking here is well thought out. Okay, so with these choices, I will generate the primal. So let us see, and now we are supposed to substitute this u and v and generate the primal iterate. Okay, so we are supposed to substitute, I guess. So let us call this equation, let us say A, and this is equation B. So from B and rearranging terms, so from B we have k diag of VL is pi tilde 2l minus 1 by diag of UL. So I guess we get it from B. And what I have done, other thing is I have also did a little bit of notational change, that I shift L by L minus 1. So let us see if things work. So k diag L become L minus 1, so then we become VL, pi tilde 2L plus 1 become 2L minus 1 with the choice L minus 1, and diag of UL. Okay, so that's correct. Because these are iterates, I am allowed to go forward or backward, it doesn't matter. So now with this choice, let us look at pi tilde 2L. Okay, so and we have pi tilde 2L is pi tilde 2L is there, right? Diag of UL plus 1, so I have just copied it here as well. So diag of UL plus 1, and then K diag of VL. Okay, so that's I'm using A now. Okay, so pi tilde 2L diag UL plus 1 plus K, like so. This is from A. Okay. And we have K diag VL from above, so we are going to substitute that. So let us call this C. So from C we have pi tilde 2L is diag of UL plus 1, and K diag VL we will substitute it by pi tilde 2L minus 1. So this is pi tilde 2L minus 1 divided by diag of UL. Okay, we just substituted K diag VL. So if we had the primal in the view, we would have known how we are going, right? Because we have to arrive there, right? So basically the primal, if you remember, those were in pi only, right? So those were written in pi. Okay, the left pi is obtained from some updates of the right pi, and P was involved there. So we are supposed to get those terms. Okay, and we can also do a substitution for UL plus 1 and UL plus 1 from here, which is P by K VL. Okay, so I can also do it right here. So okay, let me do it one more. Okay, so this is diag of, now UL plus 1 is P by K VL. Okay, and then everything else 2L minus 1 by diag of UL. Okay, and this came from star double star. So we have this now. Let us okay, so what I did is the next is I took the diagonal UL inside. Okay, and we can do that. So the diagonal UL inside the first denominator of the first diag. Okay, and because my goal is to bring in UKVL form. Okay, so that I observed in the first diagonal, but then it will be not exactly diagonal because the denominator is the vector, so it will be just V for the right one. Okay, so let me do that. So this is diag of P by diag of UL K and then VL. Okay, and this is pi tilde 2L minus 1. Okay, so we have to verify that the denominator on the denominator diagonal UL can be observed like this. If we bring in like this, then this. So basically what we are trying to say is that this term, I mean the whole thing, this term is same as this term. Okay, so you can verify this. Okay, these are some vector matrix thing. Okay, so you can verify this separately. So we can write like this, and then this whole thing could be written as pi times 1m. So this is diag of P by pi tilde 2L minus 1 and then 1m, and whole thing pi tilde, I mean sometimes we put lambda to denote that it's entropy regularized form. Okay. So then diag of ul k vl according to our notation, it's if you remember, then this recall we had earlier written 2l plus 1 is diag of ul plus 1 k diag of, so this is k diag of, so this we wrote before, l plus 1. Okay. So I believe because it's l minus 1 form, yeah, because here we are looking for ul k vl. Okay. So we did one shift to the left, so meaning l was replaced by l minus 1, so then it becomes 2l minus 1 ul vl. Okay. So 2l minus 1 ul, but then here we had in vector form, not the diag form, so it means that it must have been multiplied by a vector of all ones, so that it became v. Okay. So that's what we did. Okay. And it seems that this is the primal, if I'm not wrong. This seems to be very similar to this, right? So that's it. So and then we can do the same argument for the other one. For similarly, we can do this for the other choice. Just for completeness, I will do it very quickly. Okay, but it's the similar case. Okay. So if you feel, you can watch the video again, but I'll just do it very quickly. Okay. So similarly, diag of ul plus 1 k is pi tilde 2l by diag of vl, and this becomes pi tilde 2l plus 1 is diag of ul plus 1 k diag of vl plus 1, and this implies pi tilde 2l by diag of vl diag of q. In this case, now we have q, k transpose ul plus 1. Okay, you verify this as an exercise. I'm just writing this quickly. So this is diag of q divided by diag of vl k transpose ul plus 1 pi tilde 2l, and this becomes finally diag of q by 1 n transpose pi tilde 2l and then pi tilde 2l. Okay. So these are this was last one was odd iterate. We have, so you can check all this, and especially this one, because previous one we have already checked. This was odd iterate, previous one was even iterate, and they matched with the original primary iterate. So essentially pi tilde is nothing but pi. With the Sinkhorn algorithm for the iterates of u and v, it's the same as the original algorithm. So now as the next thing that we want to do is, now remember our goal is generative modeling, right? So now the fact that we have done all this, how does it help in generative modeling, right? So let us build a generative model out of this. So now we go to generative modeling and wrap up this part, and then we go to VAE in the next class. Today it's not possible. So now we'll look into the generative modeling, and the paper is learning generative modeling with Sinkhorn divergence. And AI Stats 2018. These are not too old, okay? Only 4 years old. So let us build a generative modeling. So essentially what is needed is just write some algorithm directly, okay. So because the idea is all in place. So algorithm, the first step, draw mini batches x1, x2 dot 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 xb that follows the distribution p. So let's say these are your cat images, okay, and then generate some from your not so well trained generator. It could be neural network, let's say. So let us say you generated, initially it will generate very bad stuff, but let us say you generated some of these from your generator. Theta is the parameter for the neural network you will use, and then approximate. So now you will compare, okay. So approximate, you will build a distribution out of this histogram, and then you will plot, compare with the versus time distance. So approximate this. So the hidden, the underlying distribution could be continuous, and obviously in computer we can work with samples, so discrete case. So we are hoping that this discrete form is also equivalent, close to the discrete case. So we define this discrete as a histogram. So the p hat is a distribution that we created out of these samples. So basically PMF. So 1 xi equals to x, I equal 1 to b, and then p hat theta x is 1, y1 is y, I equal 1 to b. Okay. So given samples, we can always create a distribution based on the sample like this. So just count number of times that x appeared in your data and divide by b, so that gives you the probability values. So you do this for both p and p theta, and then the good thing about Sinkhorn algorithm is that now it can give you a good estimate, faster estimate of W1. It will give you a comparison of this. So the third step is estimate W1 p hat theta using Sinkhorn algorithm. And then the fourth step is compute the gradient which could be, let us say, theta is updated as theta minus eta grad theta W1 p hat theta. Okay, so that's it. Okay, so what will happen is that as long as p theta is not well learned, it will keep optimizing for theta, it will keep updating theta, and the expectation is that at some point there will be an optimal theta star which you will put in p hat theta star, and it will be very close to the original distribution, let's say, of the cat distribution. Okay. So later on, since your generator is learned, theta star has been found, you can just sample from there, right? So the next step, generation process, will be sampling, because you have learned the distribution, and the next step for you is to sample. And this sampling process, maybe you could have also encoded in the neural network itself, in the sense that you create a push forward from JAD, and then from there it gets transformed into P. Okay. So let us write an architecture of this for a clarity on this. So I will rub this because this architecture will be long. So let us write the diagram of how things are. So what is happening is, so I have Z1, Z2, and I can sample these from standard normal. Okay, so I know how to sample these guys. It goes through neural networks. Okay, so let us say this, and then neural network usually have couple of layers. So let us build some layers. Okay, so it goes through this. Basically, it does linear combination activation multiple times. Okay, so okay, and then it outputs vectors x1, x2, xm, and then this is your input data y1, y2, yn. I hope my notations are not the other way. The way here I am, okay, I hope it's not. So way it is saying like this is like the CAD distribution now. This is my input data, okay. And this is something I have generated right now, okay. And obviously it came from, let's say, some known distribution. It went through this, and initially thetas are very arbitrary. The weights of the network is a parameterized network, and theta 1, theta 2, theta 3. These are the things you will tune. Okay, so you generated something which is a garbage initially, okay, and this is the actual distribution. You will compare them using Wasserstein distance. If the cost is bad, you will tell gradient descent that go back and change your theta so that the loss is minimized. So it will go back, change this. You do the process again, you generate again. You get another set of CAT images. You generate again, and you compare with the Wasserstein distance. The cost is high. You again go back and tell the network you change your parameters, okay, and then you do this repeatedly, and ultimately it should learn. Okay, so a more detailed diagram is just about calculating the Wasserstein distance, nothing more. Okay, so here it can go into some the cost block, okay, and this also goes into cost block, and this cost block we have seen is xi, yi, okay, and then from the cost we know that we build a matrix K which is given by minus C times lambda. So let us say C is a matrix now. So from there we know that we compute a matrix K, and from K we know that we run the Sinkhorn algorithm that we have just seen. So here in the Sinkhorn we have odd and even iterates. So I can have these, and then pointwise divide, and then pointwise divide, and then I can have UL plus 1 as an output. This output again iterates back to UL. Okay, so these are the abstract steps, and this loop itself can run for a number of Sinkhorn steps, which is L minus 1, let's say. And out of all this, we get some U and V. So basically, we form this diag of U, K, diag of V, which is supposed to be our joint distribution. And then since it's overall cost, so I will multiply by, because it's a sum of CXY. So I want to make this as a full thing. So and cost is also there. Sorry. So cost times the pi dot pointwise multiply with this, and flatten them by 1 transpose 1. So this is your cost. Basically, this is sum of those pi xy c xy, given that pi xy was this. So that's what we are trying to do here. So this is your cost, but this cost is parameterized by theta, because in all this U and V, they are all connected via K, C, and if you follow this arrow, there are thetas lying here. Okay, so overall, since the cost is built over all this, there is a dependency on theta that we are not writing, but if you want, we can write U sub theta. This U and V have dependence on that. So in machine learning, when you do a lot of these deep learning stuff and so on, you will do a lot of architectures like this. Okay, this is your essentially plan and algorithm, everything. Okay, and let's say, for example, another plan is you don't know the cost, let's say, because initially you can say that, okay, let us go with the Wasserstein's cost. Okay, and let us say this was norm x minus y, But then the good thing about supervised learning is that things sometimes when you are not sure about, you also put a weight there. Okay, so what if I parameterize these guys also? Okay, so I will say, okay, I'm not very sure about these costs and what is a optimal cost for this problem. Then why not parameterize this by, since I don't know, also let x pass through some neural network, y pass through some neural network, okay, and let them learn on its own what was the optimal way. Okay, so let's say I used theta before, so let's say this is another neural network, this is phi. Okay, and then I will say instead of the cost, I build a neural network here as well, and it does a little bit of tuning, and then it gives me phi xi, phi yi. Okay, so in the original Sinkhorn paper, they did this additional step. They said that I'm not sure about the cost to be this or square, or because there are so many ways to take a norm. Okay, and I believe that just doing this is also not enough. They did this, but what I'm saying is like there could be square also, right? So there could be a possibility to play here as well. Okay, what they did is like this could also be used as a form of a little bit of dimension reduction maybe. So your original x may be projected into some something smaller. So you are going with some smaller vectors and so on. So this could be another advantage. So they have put a later on as an additional thing, they put this parameterized network as well here. But then if they put this parameterized network here, it becomes not just the mean problem, because this goes into the cost. Okay, so now this cost, this goes into the cost, so basically you have to maximize over this phi. Okay, so you are maximizing the c over this phi, so overall it becomes a min max problem. Okay, so there is this additional optimization you have to do because it becomes a min max problem. But if the cost matters a lot, then maybe it's a good idea to do this as well. Okay, yeah, no, it is supposed to be learned. It is supposed to be learned. So obviously we put a phi here for the fact that we will learn it, right? So when I do a backprops, I come here, I got a cost, and then it will be phi here. Now as I said, this is minus c here, so it will be min and then max over phi. Okay, phi, and then we have to do backprop here, we have to do backprop here. So backprop means computing gradient. Okay, so backprop means that via I compute the gradient via backprop, which is used in the gradient descent ascent to tune the parameter basically. So backprop is, that's what it means. Okay, for those who are not aware. So we can have this additional step. In fact, they did this, and it's a min max problem. So then you have to do gradient ascent and descent, descent with theta, ascent with phi. Okay, that's an additional step they did. So you can pick up some of these as a project and implement this yourself and see. I mean, as a project, it could be interesting to show what just a comparison itself could be interesting. What if you took a square, okay, one norm, or you put a generic norm, or what if you did some dimension reduction after the passing through the neural network? What is the effect of that on the generation task? So you can play around this as a code. Okay, so essentially this part is done. Optimal transport, generations, and all this. I am pretty much done with this. So I think today I have a restriction that someone else is supposed to come, so I think I will stop today.